introduce our speaker today, and it's really a great delight to do these introductions. But I also have a slight additional point more to the students and early career folks. If you can, as you're looking for jobs down the road at some point, find not a department, but a community of scholars to work within. Find a place with abundant collegiality, thoughtful scientific pursuits, and great communication and sharing of ideas at colloquia of this sort, seminars, and in the classroom. But one thing that might be a little bit more challenging to find is when you arrive at this new position, is a contemporary colleague who not only shares your interests, but encourages you in your pursuits within and outside of work. Someone who first thing in the morning is as eager as you are to chat about an upcoming snowstorm, even if it's 2 or 3 weeks out. And maybe saying eager might be wrong, but that may be too strong a word, but politely entertain or tolerate such a discussion. Or talk about research ideas that popped up in your head or the goings on in the news. And I've been fortunate in my career to have such a colleague. It's my pleasure to introduce my friend and colleague, Professor Jonathan Martin, who is beginning his 26th year in our department, began this September. John has been an exceptional department citizen, helping along with many other colleagues, both past and present, to make this AOS community the wonderful place that I've just described it as being. Now, as many of you don't know, that despite our differences in speech, John and I were born in Massachusetts. Me in western Massachusetts, Northampton, and John in the east near Boston. I suspect that gives rise to his accent. Different between east and western part of the state. I've known John for 25 years and know him well. I can hear his footsteps even before he leaves his office, coming down the hallway. He is, as we all know, a huge sports fan, and I share his sincere disappointment with his beloved Yankees not making it to the World Series. His interest in weather systems is widely known, and I share his grief that the tropical cyclone season is waning in the Atlantic. But seriously though, John is a polymath within our field and beyond, a superb educator, researcher, and scientific historian. His interests range from the structure and dynamics of extratropical cyclones, primarily, as well as their attendant fronts and the associated polar and subtropical jets. He's particularly keen in the organization of vertical motion as it pertains to precipitation and cyclone development. He has recently completed a manuscript on a historical giant in our field of dynamical and synoptic meteorology, Reginald Sutcliffe, and will, I am certain, find a publishing home for this sure to be delightful and insightful text. John has an interest in climate time scale phenomena, including the annual cycle of the areal extent of 850 millibar cold pool, the meanderings of subtropical and polar jets. How does their waviness vary across time scales from subseasonal to seasonal to interannual? Are changes in these measures a measure of climate change? If so, what might they suggest? Today's talk explores the trends in the waviness of the polar and subtropical jets. I'm really looking forward to hearing this talk. And so I present my friend and colleague, Professor Jonathan Martin.
Thank you so much, Michael. That's such a generous introduction, and I definitely agree with everything you said. It goes the other way. You've absolutely been one of my very best friends in my whole life. And almost all of that small collection are people who are interested in the weather, and you're at the top of that list. So thank you very much. For the past few years, I've been thinking about how to measure the waviness of the mid-latitude flow. And this might seem like a strange obsession, but it's really related to some of the things that Michael just talked about. A number of high-impact weather disturbances are a result of high-amplitude flows in the mid-latitudes. Few examples. This one I remember, it was hovering around or above freezing on Christmas Eve, the 24th of December, 1983, where I grew up. The next morning it was -5 at my house. And so this is an extraordinary cold air outbreak that occurred in December of 1983, and the geopotential height lines at 500 millibars every 60 meters, the 540 lines in red. It's a high amplitude flow that led to this particular event. Then in early January 2014, many people in the room will remember that this cold wave was exploited by our shock-addled media. And the word polar vortex was let loose upon discussions of all subsequent cold air outbreaks after this one. But again, very high amplitude flow, and we were really frigid in the early part of January 2014. So I've been interested in these things for a number of different reasons. Now, the amplitude of the flow is a characteristic that can sometimes lead to persistence of the types of structures that lead to these high impact events. And some insights about that come from the Rossby wave speed equation, where it's clear that the intrinsic phase speed of Rossby waves is negative. And if k squared plus L squared is quite small, then you can get quite large. You can get very slow propagation to the east. So long waves tend to make slower eastward progress. And there's other physical ways to uncover that result, but that's an interesting result that coincides with these high amplitude flows. And currently, in the last 30, 40 years, we've been experiencing unusually rapid warming at high latitude. And some of this, it wasn't first exposed by Jennifer Francis and Steve Avers, but they took this idea as a starting point to launch a hypothesis about what might be occurring in response to the Arctic amplification that's characterizing the last 40 or so years. So these are thickness fields from 1,500 millibars, anomalies, over the last 40-ish years, as I said. And you can see that the high latitudes during the cold season, I'm showing October through March in these two panels, is a little bit, the anomalies are larger at high latitude than they are everywhere surrounding there. And the idea they had was that this might serve to elongate, by increasing thicknesses at high latitudes, this might serve to elongate otherwise already high amplitude flows by pushing the geopotential height lines a little bit higher to higher values at high latitude underneath the thickness anomalies. And the higher amplitude the flow gets, the slower eastward progress they make. So they kind of set up an idea that there may be a feedback between warming at high latitudes and increased wavelength, and as a consequence, slower progression, and maybe an increase in the intensity and perhaps even duration of these high impact weather events. Elizabeth Bonds came along and said, well, you know, maybe some of those results are a little too dependent on the methodology. She was among the first to point this out, that the positive trend in the meridional extent of waves over the North Atlantic and North America may have been artifacts of the methodology that was employed in that Francis and Avers study. For instance, Elizabeth talks about this Cmax min. So this is seasonal maximum and minimum of individual longitudes of the geopotential height at 500 millibars. So over the course of a 90-day season, what at a given longitude is the maximum geopotential that's ever observed, and what's the minimum geopotential? Or for a geopotential height line, sorry, what's the maximum latitude that it ever finds? What's the minimum latitude that it ever finds? And this is akin to what was used in the Francis and Avers analysis. But it never really looks at individual waves. So she also did an analysis of what she called day max min. So this is on a given day, what's the maximum latitude that a geopotential height contour might make on that day, and what's the minimum, and then this measure would be a measure of the latitudinal extent of the waves. And it turns out that when one does an analysis of either the seasonal maximum minimum versus the daily maximum minimum, there is a trend in the seasonal maximum minimum, but there's no such trend in the daily one. And that indicates that individual observed wave extents maybe have not been trending at all. And that's a reasonable refutation of the original analysis. Now, at the same time that this work was going on, I was interested in measuring the areal extent of cold air at 850 millibars, minus 5 degrees particularly. And I found that there was a systematic shrinking of the Northern Hemisphere wintertime cold pool. And while I was talking about that work in a department seminar at that time, 2013-14, Matt Hitchman suggested, why don't you look at what the equivalent latitude of any one of these isotherms is? And I said, well, that's kind of an interesting idea. You just calculate the area that's enclosed by the isotherm, and then imagine that it were zonally oriented all the way around the hemisphere, and you get an equivalent latitude. I thought, that's kind of a good idea. And I started to do that with the isotherms. Then Steve and Jennifer and I were talking about this wavy problem, and it occurred to me that you could use a similar idea to try and evaluate the waviness of the flow. And using geopotential height lines like this right here as an example from January 2014. So if you take any one of those height lines, this is the 552 decameter line, then that is going to circumscribe a certain amount of area, and that area is exactly the same that's contained poleward of this cap, this zonal cap in red. And I thought to myself, well, a measure of the departure from zonality of this isohyps is just how long is the blue line divided by how long is the red line. And so the more wavy the flow is, the bigger that number is going to be. And that seemed like a reasonable and very intuitive way to think about this. And this is an idea that has been used for decades in geomorphology for looking at how sinuous rivers are. Here's a picture of a portion of the Ganges, very sinuous. And what you do is you just measure the length along the river itself and divide by the shortest distance possible between endpoints. And there's no reason at all why you can't do this on the sphere. And so I thought this would be a useful, very simple tool to make measurements of the daily difference in how wavy the flow is. And so that's what we started to do. And on this particular day, as the example, the sinuosity ratio is 1.271. So the blue line is 127% longer than the red line. even though they enclose the same area. And if you take an aggregate of 5 different geopotential height lines chosen somewhat carefully at 500 millibars to make sure that they generally contain the highest wind speeds during the cold season, then you add up all of the lengths of the blue lines, add up all the length of all of their equivalent latitude circles and divide the two, then you can get what are called the aggregate sinuosity. And then you can calculate that every day, and you can calculate a seasonal average. And when you look at the seasonal average from the NCEP reanalysis data from 1948 all the way to, I think I went to 2013 with this data set, there's no trend at all in that particular measure. And that was somewhat disappointing, but you know, you can't always get what you're hoping to find, and you learn something when you don't. So this was an exciting result in a different way. But there's no particular trend in the sinuosity. And this rather backs up the idea that Elizabeth Bonds suggested, since this is really based on day-to-day variability averaged over each season, that there's perhaps no trend in the meridional extent of the waves at 500 millibars. But it occurred to me that maybe that isn't the right way to look at this problem. That perhaps by focusing on some mid-tropospheric height field, that we might be just looking at this in a slightly skewed way. And so I thought maybe there's another way to look at this problem, and directed my attention to the tropopause level jets, which are in fact, of course, a more overtly dynamical phenomena than geopotential height lines. So that's where I went next. And if you go to the jet level, you have to remind yourself that there's really 2 distinct species of jets at the tropopause in the Northern Hemisphere cold season. One is the polar jet at higher latitude, and another is the subtropical jet. And this is an example from the early part of the spring, the late part of the winter from, I think, 2010 or 11. And if I take a cross-section along this line, A to A prime, I don't think anyone would first of all dispute that there's 2 separate species of jet in this picture. And then if you take that cross-section, maybe the shading didn't come out, but it's only light, I guess. From 340 to 355 is where the subtropical jet sits in isentropic space. And from 315 to 330 is where the polar jet sits in isentropic space. And notice that both jet cores are on the equator or low PV edge of a really strong horizontal PV gradient. And that's not true at every isentropic level, or at every spot on one. Here at 350-45, there's almost no horizontal PV gradient right in this location, the saddle point between the jets. But over here at 345, there's a pretty strong one. And so trying to put together both the isentropic location of jet cores and the PV gradient characteristics, Andrew Winters and I were thinking about this one winter, one summer, 2012 or 13. And I give him a lot of credit for helping to figure this out. But we ended up looking at the NCEP reanalysis data in these layers and found some interesting things. That's a reasonable spot to find the 2 different jets. And the reason why the jet is kind of an interesting, or the PV gradient is related to the jet, you can think about just by considering the QGPV, which it's a reasonable proxy for the full PV, especially at higher altitudes. But it's effectively a 3-dimensional Laplacian operator operating on the geopotential height. And so if you take gradients across the flow of the QGPV, then with dQGdN, then that's going to give you a Laplacian operating on dphi-dN, and if you substitute from the natural coordinate expression for the geostropic wind, you find out that anytime you get a large gradient in a cross-flow QGPV, you have to have large geostropic wind. So there's a really theoretical basis for the correspondence between strong horizontal PV gradients and maxima in the wind speed. And so it turns out that the jet actually flows along isotels, lines of constant PV. Not in the same way that the geostrophic flow flows along geopotential height lines, but in something that approximates it. And so that's a reasonable way to begin the hunt for jet core maxima in PV space and in theta space. The way we did this in Croy Christensen's thesis, and this was work that was that Zach Handlos had a hand in as well at the end, is we looked at several, almost a dozen, maybe more than a dozen, isentropic layers from the NCEP reanalysis data, and we calculated the minimum, or the zonally average distance, delta y, between the 1 and the 3 PVU contour in each of these layers. And you find that there's local minimum in that distance, so a local maximum in the PV gradient, in the 315 to 330 layer, and there's another one in 340 to 345. And then there's a minimum in between. It's not a substantial difference, but it's a significant difference, as it turns out. And then if you look in every, sorry.
Can you describe what that is showing?
Yeah, this is showing the zonally averaged meridional distance between the 1 and the 3 PVU contours. So it's giving you a measure of the gradient. You know what the difference in theta, PV is, you're just looking at the denominator for the gradient itself in the radial direction. And the scale goes from highest values to lowest. So these are local minima in the distance, maximum in the gradient. And then there's a little bit of a curve back, and then there's another local minimum in the distance. So these two layers, or these layers, represent regions where, in a zonally average sense, throughout the whole 300 to 370 Kelvin layer, you have local maxima in the zonally average PV region. So those are where the jets ought to reside. And then vertical columns. Every vertical column in the NCEP reanalysis data measured in isotropic space, we find the maximum wind speed in the column. And in most instances, the maximum wind speed falls also in columns in those layers within the column. So there's a couple of different ways, and this is an expanded cold season, November through March. And so there's a couple of ways to feel confident that 315 to 330 and 340 to 355 are the isentropic housing for the polar and subtropical jets. And so if you go back to a more conventional view, 300 millibar wind speeds, it'd be really nice if you could get a picture of what the core of the jet is around the hemisphere. Because then you might be able to, if you can objectively identify the spine of the jet, it might circumscribe areas and you can see where it's going. I might be able to calculate the sinuosity of the core of the jet. And if I can get two different species, that's even better. So a determination about where the core of the jet can be made by the human eye-brain supercomputer. You can draw a line through the center of the isotope maximum. Right? And with the Christensen et al. Identification scheme, you can even determine which type of jet it is on a given day. So the red lines are subtropical jet cores, the blue lines are polar jet cores, as a schematic. But you'd really like to know how can you connect these? These are unconnected segments. How can you connect them to make them look like that, perhaps, around the hemisphere? And can you confidently do this objectively is the challenge to try and measure the waviness of the jet. So how are we going to do that? Well, we're going to take advantage of the fact that the jet flows along the isotops. And we're going to use the circulation theory to figure this out. And so by going through a series of isotelic values from 0.1, and from 0.5 to 5.0 PVU. So 0.5 is way too small to be at the core of the jet. 5 PVU is probably too high on almost every day. And that's why I chose that range to begin with. Then we just search through each one of those at 0.1 PVU intervals. So there's 46 different tests that are done on every scene, every day, every daily average. And then you find out which PV isotel has the greatest average wind speed. So the maximum circulation per unit length, the line. Correct.
What's the difference between isotel and isentrope?
An isotel is a line of constant PV in an isentropic layer.
But an isentrope is a line of constant PV too.
No, an isentrope.
Oh, isentrope, okay,
Yeah,
no,
yeah.
you're right,
Yeah.
yeah, I got you.
So we're trying to find the isotel that has the largest circulation per unit length. And that will be the core of the jet. And it makes sense because it'll have to have, by definition, it'll have the greatest wind speed along the whole thing, continuous around the hemisphere.
Could I ask, is there a special case if a contour goes over the pole, is that hard to treat algorithmically?
I don't know.
A surge over the pole and it goes like, oh.
I don't know.
I suppose you could go on a meridian and then count that extra distance to the delta y?
No, the
Or
distance.
it just doesn't happen very
The
often?
distance, no, it's not that it doesn't happen very often. The distance calculation is not compromised by that. The area calculation isn't either. And I don't know if the circulation is, but I had to renovate the circulation part of my calculation this summer because it was an easy mistake to make, which I made. I'll point it out in a minute. So I don't know if there's any such problem. It doesn't seem like it from the data. So that's what we do. And so that in this bundle, schematically, of course, it should be that isotel that's closest to the core of the jet. And you'd imagine that your algorithm would find that one and report that for that segment. But if you're doing the whole hemisphere, you have to weigh it against everything else that's going on in the hemisphere. So gridded data comes, at different grid points. And if you have just U, V, and PV, so you really only need U, V, and T to do this analysis. That's it. And that's among the most basic variables in any reanalysis data set, I think. There's no humidity, nothing like that. So U, V, and T, and that'll give you PV and UV at each one of these grid points. And then you search through all your different isotels. Let's say that this is 1.5 PVU, and these values are higher, the ones that are gray shaded. And then you can figure out what the average wind is along this segment, and therefore you can calculate the circulation segment, add them all up, and you can figure out what the total circulation is for that particular isotel, and then compare it to all the other ones that you do. And that's kind of how we go forward, march forward into this. And if it happens to be the one with the greatest wind speed on average, it's the core isotel for that day. And the core isotel is not the same every day for each species of the jet. And I'll show you that in just a minute. So let me give you an idea of how this works in a particular example from January 2014. There's nothing particularly interesting about this day. But first, these are the ice attacks in the subtropical jet layer, 340 to 355 Kelvin. The black line, and they start at 30 meters per second and get larger in size. So there's wind speeds that are in the data but not portrayed in the contouring. This first black line is 0.5 PVU. And you can see that it's not anywhere near the center of the jet in the Pacific. It's nowhere near the center of the jet in North America, nor over North Africa and Eurasia. So it's not a good fit. Luckily, it doesn't come back that way in the algorithm. And 1.5 is a pretty good fit for the core of the jet in the Pacific, but not over North America, not really so good over North Africa, pretty good over Eurasia. And you can see, if you keep on going to the next and next lines, the fit gets better and better around the hemisphere. 3.5, it's maybe strayed a little too far away from the core of the Pacific jet. It's a little closer to that. It's a little forward of both of the Eurasian and North African jets. 4.5 is even worse. It turns out the actual value is 3.2. That comes back with the maximum average wind speed along that isotel in this layer on that day. And that pretty much fits the eye test, I think. It's pretty darn close. And so anyway, that's how we get the isotel, the core isotel, by a search like that.
What about aggregate Ertelian sinuosity?
I'm sorry?
What about aggregate Ertelian sinuosity? You average across a layer.
I hadn't thought about that.
You did it with the height contours.
Yeah, because I didn't have an alternative. I wanted to make sure that I wasn't leaving anything out. This one is trying to be more precise, and so at least for now, there's no substantial difference very often between 3.2 and 3.1 or 3.3, but there is some difference. So I'm going to take the maximum value and see what that gets me. Maybe it isn't a bad idea to try 3 of them around the central value or something.
But it looks like it's leaving something out by Africa over there.
Oh, you'll see what I mean about that, yeah. So that's right. That's a concern, right?
Yeah.
Look at this. Here's an example in the same layer but on a different day, and the core isotel is shown here at 1.4 PVU. Again, it looks like something's missing here. This whole axis of maximum wind over Scandinavia and the Northeast Atlantic, what's that doing? Well, if you go down to the underlying polar jet layer, that's actually the core of the polar jet in that region. And then this is just the upper level vestigial part of that core. Also, here's a piece that seems orphaned from the 2.2 PVU core isotel in the polar jet layer over North Africa. But that's right in the heart of the overlying subtropical jet. So in many such instances, and I can't say that every instance is like this, I don't have the computing skill to make an algorithm that'll test all of that, but in many such instances, what looks like it's orphaned in one layer is actually part of another layer, and you can kind of find evidence for that.
So it seems like, extending on what Matt was saying, maybe you should think about a family of isoplus in the vertical now. Really, you've defined some vertical layers if you're looking at this.
Yeah, that's right. And in fact, doing that might allow for a little bit less reliance on the objective identification of those houses. And they may differ from reanalysis data set to reanalysis data set, as I think you'll see.
You'd be able to say, here's an isotrope that has both subtropical jet. You'd be able to look at families of the 2 jets.
Yeah. That's right. So there's a whole bunch of different ways that one could try to do this analysis, and I'm showing you what I've done so far. But those are good ideas. As I mentioned before, the core isotel will not have the same value every day by construction. That's just not what we're looking for. We're not mandating that. So here is from the NCEP reanalysis over 66 years of the analysis. Here is the distribution, number of days that the core isotel was at 2 PVU. Is something like 378 or 380, and there's a nice distribution. It peaks right around 2 PVU, which maybe isn't unexpected. But once in a while, low values are in there, and once in a while, somewhat high values are in there. I think it's something like 70% of it is from 1.6 to 2.4 or something like that. So it's a large part of the distribution. The polar jet core isotel is much more narrowly distributed, and it's maximized around, 1.3, I think, and there's almost, there's more than 900 days that do that. Surprisingly, and I'll show you this later, it doesn't matter what reanalysis data set I've used thus far, 0.8 never shows up. That's really weird, but it's true, and I don't know how to explain it. But I've seen it in this data set, the NSEP reanalysis data, and at least 2 other ones. So that's weird. Okay, so here's our 3.2 PVU on that day. So there's an area that's enclosed by the black line, and then there's the equivalent latitude for that same area, and the sinuosity for the subtropical jet on this day, based on the spine of the jet, is 1.53. So that's how I get to my conclusion about how wavy the jet is. And then it's a relative measure, of course. You're either larger than 1, you're never lower than 1, and then how much larger than 1 gives you an idea of how wavy you are. So once you have this, you can calculate daily time series for a season, you can calculate long-term seasonal averages, and then anything you want you can kind of do by looking at this measure. So here is what the NSEP reanalysis data suggests has been happening since 1948 to the almost present time. Subtropical jet, seasonal average sinuosity of the subtropical jet has been, there's a lot of interannual variability, but there's a trend that's 99.9% significant. And then the polar jet has even more interannual variability, but the trend is also highly significant. I think it's almost exactly at the same level of significance. So that's what the NSEP reanalysis data suggests, is that the polar and subtropical jets measured in this way are getting systematically wavier. Maria?
It's hard for me to tell by eye now, but is one of them steeper?
I can't hear you.
Are one of the trends steeper than the other?
I don't remember that.
Okay.
It might be true, but they're almost the same. I don't know if they're exactly the same. Yeah, I don't know. That's a good question. But I have it in my data somewhere. Now, don't forget, if you take the 500 millibar aggregate sinuosity, there's no trend at all. It's on the same scale. So this at least seemed to suggest to me that maybe looking at the mid-tropospheric height field is not really telling you the story. And that was a suspicion that I had that motivated this, and it seems confirmed, at least from this reanalysis data set, that maybe that isn't the best way to look at this problem. But one might wonder if, in a given cold season, the waviness of the subtropical jet influences that of the polar jet, or vice versa, or do they pretty much operate independently? And that's, I guess, a reasonable question. And we can answer it a little bit, at least so far. I've done it with the NSEP reanalysis data. Here's just one particular season, 1990-91, and not picked for any particular reason. But the daily time series from December 1st to the end of February of the polar jet waviness, measured this way, and the subtropical jet waviness. And they're not correlated at all, these time series. And it turns out that that's generally the rule. In 35 of the 66 winters that I've done in the analysis, the correlation is less than 0.2, like it is here. And in only 10 of the 66 winters does the correlation magnitude exceed 0.3, and only a couple of times does it exceed 0.5. So it seems to me generally, and this is not fully developed yet, but generally it seems to me that there's no particular systematic influence between the waviness of one species and the waviness of the other. That doesn't seem to be the case. Although there's clear evidence that there are times when the two jets will phase, and that's a function of how wavy they are, but they don't seem to tug on each other in any systematic way.
Is the denominator held constant, or in the equivalent area idea is that does the disk change in time? The denominator part of the ratio. What is that?
Yeah, the equivalent latitudes?
Yeah.
Trend in the
Oh, there is in the seasonal cycles. There sure is, yeah. Yeah.
secular trend.
So that would,
But that trend will be the same, in every single year on February 1. So when you look at a whole bunch of these, then there shouldn't really, that should be kind of filtered out. Right.
it might be interesting just that trend by itself. It's like
Yeah, I'll show you an example of that trend in a little bit later. Not particularly in this context, but in something that's related.
John,
Yeah,
I was curious, so this is 90-91.
right.
Are there any times when you've looked at this in which you do see those two curves kind of trending together for a few weeks, a few days, in terms of the...
Whole subsets of the
right.
single season? I don't know. That's a good question.
It might be interesting to look back, if the records must exist for like anomaly correlation scores. I wonder if there's a predictability aspect you might be able to
Oh,
tease
yeah.
out of that, if
Yeah.
there's
greater or a strong decorrelation, even though this isn't a really strong correlation?
Mhm.
Is there something about rating the correlation between those that says something about predictability?
Yeah, that's a really good question. And that would be, you need to have I have all this data that I can do that with, as long as I have the dates, you know, that you might want to
Or just
test.
get the time series of the
Yeah, right,
correlations,
right, yeah.
So in terms of your hypothesis for why this happens, you're thinking in terms of what you presented earlier with the polar amplification compared to the mid-latitudes?
No, I'm divorced from any explanation today of any reasons. That's a good question, but I'm not trying to explain it today. I'm trying to just report on what I've learned thus far. So I don't have any sense of what might be underlying this. So that's where I stand, yeah. I think that idea has trouble, but I don't know if it's wrong or right, and I'm not going to make a statement about that. Here's something that's kind of interesting. You know, since you are calculating the circulation around the hemisphere at the core of the jet, and you're finding what the core of the jet is, you can actually look at what's the trend, if there is any, in the average wind speed at the core of the jet over the course of the season. And it appears that there's no trend at all. The subtropical jet has a lot of interannual variability, but when you try and put it through, a simple Pearson correlation, you don't get any trend, but it ranges from about 46 to 50 meters per second, sometimes higher than that, sometimes 54 meters per second for the seasonal average. The polar jet in the NCEP reanalysis also has no clear trend. There might be, if you subdivided it, there might be a little bit of one up to about the time the satellite era comes in, and then the satellite era is pretty flat. So it doesn't appear that the jets are speeding up in the NCEP reanalysis data. It appears they're just getting wavier, which could lead to hypotheses about what's driving it, but I haven't gotten there yet. Here's the annual cycle of this. This is which later now, let me remind myself. This is the polar jet. I can tell by the high values too. This is the annual cycle, unsmoothed. And so you can see it reaches its minimum sinuosity right around the time of the midwinter suppression, early February. That's not perhaps surprising. And it's a little bit wavier early on, and then it recovers and starts to get wavier as you enter the early part of the spring. This is superimposed upon that seasonal cycle is the daily value for 1990 to 91 of the sinuosity of the polar jet. Sorry, it's kind of extreme in the way that I've done it, but I did that so that I could color in excess days and minimum deficit days. And if you add up all the excess, subtract all the deficit, you get an integrated departure of 10.63 units for that season. And then if you do that for every season, and you figure out what the average departure is, and the standard deviation of the averages, you can start to look at some interesting characteristics of different seasons compared to one another. Okay, so that's what I want to show you next. Here is a scatter plot of every season in the NCEP reanalysis data, plotted on wavier subtropical jets, wavier polar jets, and so less wavy and less wavy. And then it's standardized, so this is 2 standard deviations. This is 1 plus or minus, I guess it's 1 actually, plus or minus a half standard deviation around the mean, and plus or minus a half standard deviation around the mean. So that's how they show up, the 66 winters. And there's probably a number of different things that you could do with this distribution in terms of next questions. One of those might be, why is this quadrant here so full of winters? I don't know yet the answer to that. I could have looked at it before if I'd had time today. These might all be earlier in the time series, I don't know, but they certainly represent a local maximum in the number of events that occur over this space, and I don't know the reason for that. I just find it interesting. Another thing you might be able to do, though, is to take winters that are close to the average in the subtropical jet waviness, but are well above average in polar jet waviness, and then find companion winters that similarly have not very much subtropical jet waviness, but unusually low polar jet waviness. So you have wavy winters in the polar jet and non-wavy winters, and then you can do the same thing with the subtropical jet. And it's not perfect, but I'm trying to pick things from the same neighborhood, and I wanted to look at 4 winters for each species in each condition, so that I can make composites of the circulation around the hemisphere of the 4 waviest polar jet years minus the 4 least wavy ones, and vice versa for the subtropical jet.
That lower left quadrant is an interesting one.
This one
Remotely
here?
possible. It could be the Holden-Tan effect for a westerly QBO is a stronger, more symmetric polar vortex, whether, so that would be reduced waviness. Whether
Yeah.
that would translate to the subtropical jet being more symmetric also, I don't know, but there is that thing in the literature, PV westerly tends to make a symmetric jet.
Yeah, that's interesting, and I wish that I knew the dates here, and I just kind of put together a couple of these slides over the last day or two, and then today was busy with other things. I meant to try and see whether or not there was a calendric clustering, or if it was so widely dispersed that it might well be some other, physical mechanism. I just don't know.
Maybe it's, but, yeah, I don't know.
Yeah, I don't know, but.
It's only 0.2, right, so.
Yeah, that's right. Well, no, this is anywhere from
That part's
-1 or
stronger
-1.
correlation.
Yeah, oh,
That
yeah,
part.
that's right, the correlation's weak, yeah, generally. So I'm gonna just show you some of the differences between wavy polar jet and non-wavy polar jet, and wavy subtropical and non-wavy subtropical jet. So first, the polar jet, this is 1,000 millibar heights, every 20 meters in both diagrams. And so you get something that looks like a pretty strong NAO signal, positive NAO signal, roaring jet, potentially across the North Atlantic, anticyclone anomaly and cyclone anomaly, and then a broad Aleutian low, when the polar jet is wavy and the subtropical jet is about average. That's what the seasons kind of show up in the composite differences. And for the subtropical jet, when it's wavy compared to non-wavy, with a kind of standard polar jet, you get a big replacement of the Aleutian low pretty much with an anticyclone. And there's a little bit of that NAO signal, but it's nowhere near as strong as what was true about the polar jet. At 500 millibars, these structures are, at least some of the structures are equivalent barotropic. The polar jet structure, these again, geopotential heights every 20 meters. The polar jet, a wavy polar jet here has a really strong NAO signal, positive NAO, with a strong Atlantic jet anomaly across from, far northeastern Canada all the way to the British Isles, and then a strong Aleutian low. And this is kind of intriguing too, that one gets a hint of some sort of strong northwesterly flow off the archipelago in Canada into the eastern United States. I don't know if there's any connection there or not. And then in the subtropical jet, the difference between wavy and non-wavy subtropical jet seasons is this either a retracted Pacific jet, because there's a big anticyclone here at 500 millibars, or a strongly poleward deflected Pacific jet. One or the other, maybe even both interchangeably. And then you get a little bit of the NAO signal. But again, it's not as strong as the one that you see out over the, for the polar jet differences. And then even at 50 millibars, there's some differences. Before I made my correction, I had a really big difference, and I was suspicious of it. I'm glad I made another inquiry into this method. There was a strong polar vortex for wavy polar jet years, and an absolutely opposite weak polar vortex for wavy subtropical jet years. That's not the way it actually looks now. It instead looks like just different types of polar vortices for wavy polar jet versus wavy subtropical jet years. I don't know if there's anything interesting here or not. I just wanted to show it because I have it. And it does look different from what I showed before at another presentation. So now all the results that I just showed you come from the NCEP reanalysis data. And so it's really prudent to consider the same methodology applied to a different data set. Because remember, Libby Bonds' appropriate criticism of the prior work was that the methodology may have been at odds with, or may have been the source of the problem in making the answer somewhat ambiguous. And so by taking a different data set and using the exact same methodology, at least you get to avoid that and see what you get as a result. So I used the Japanese reanalysis 55-year data set that goes from 1958 to 2017, the winter of 2017-18. So that's a nice long time series. I'm biased toward the longer time series, as you can see. I want to get the longest one I can. And the JRA is at 1.25 degree horizontal resolution. The NCEP is at 2.5. So that's convenient too. I tried to formally regrid the data. I didn't even know climate people allowed this, but they celebrated. So I thought, okay, I'll try that. Seems like cheating. But the sinuosity is resolution dependent, as you can easily convince yourself. If you take a line segment through a grid box and you divide it in two, you're going to have longer length that might encompass just about exactly the same area, so you're going to have problems if you change the resolution. So I took the 1.25 JRA, skipped every other grid point because my regrid didn't quite work, and that's what I'm going to show you, the results from that, sort of a poor person's regrid. So just to remind you, this is the distribution of the core isotel from the NCEP reanalysis data, and this is the same exact distribution, but from the JRA 55 data. So in gray, as you can see, a portion of the NCEP reanalysis is in the background. I hope you can see that. And so it shifted a little bit to higher PV values. That's interesting. But the distribution still is concentrated quite in the same way as it was with the NCEP reanalysis. Here's, for a reminder, the polar jet in the NCEP reanalysis, missing, the first greatest teeth here at 0.8. And then here is the, it's missing in the JRA too, that's weird. But it's, again, shifted a little bit to higher PV values. The maximum still stays at 1.3, but the hump is more like at 1.5, when it had been at 1.2, or something like that. So in both cases, the Japanese reanalysis data pushes the core isotel a little bit to higher values.
So the gap is in both data sets.
Sorry?
The gap.
Yeah, the gap's in both. It's
sets.
also in the ERA 4.
I mean,
It's amazing, it's right. I don't know why that's the
And
case.
the outlier high value at 1.2.
It looks like the two are added together.
Yeah, that's right. Yeah.
How did that happen?
So here's the NCEP core seasonal average core wind speed from the data. You saw this before. And here's what it looks like from the JRA. So I made the NCEP lighter in the same color, but the JRA looks the same. So it's talking about the same jet, even though the core isotel is a little bit higher in both species. So that was encouraging to find that it does know about the jet and the interannual variability of the core wind speed. Interesting. And just as a reminder, here's the NCEP sinuosity and the seasonal average as a measure of the waviness. And here's the JRA. And notice I've taken a trend line out of what the polar jet and the JRA looks like. Is no trend at all. It's just exactly flat. But the subtropical jet, especially since 1980, the time in which both Francis and Baverson, Elizabeth Bonds, and others have been most interested in the satellite era, there is a trend that's just about exactly what the trend was in the NCEP data, but it doesn't exactly fit in the prior 22 or so years. But the subtropical jet in the JRA looks quite a bit more like the NCEP jet than does the polar jet. The polar jet in the JRA is completely different in this regard, but it's not different in the wind speed. It's kind of interesting.
John,
Yeah.
do you know if the data that goes into those two analyses is similar? Do they use more higher latitude data perhaps, or less higher latitude data, one side versus the
It's
other?
a good question. I should look into that. I don't know. I was told that I should use the JRA data because it's the best reanalysis data by a reviewer on this paper. The paper was rejected. I'm still working on it. And but without much reason. There wasn't any specific sense that, oh, it does this better than that, or so on. So I need to investigate that. So anyway, these are kind of some interesting results of what I found doing this analysis. And so I have a few conclusions. The polar and the subtropical jets have become systematically wavier over the last 7 decades in the NCEP reanalysis data, but not the same way in the JRA 55. The subtropical jet seems in the last 40 years to have become wavier in a similar way, but not the polar jet. Polar jet definitely has not in that data set. I wish I knew more about these data sets. You might all know that this is not exactly my particular field of expertise. I'm trying to gain some knowledge in it, and so I don't know all the ins and outs about how these different reanalysis data sets are different. But it does seem to me that the community is populated by people who advocate one over another, and they don't all share the same advocacy. So that gets me a little bit nervous. Are we using these data sets as if they were gospel in certain subsets of the community and unaware perhaps that there are these differences? All I'm using is U, V, and T. So I'm confused about that. There's no trend in either data set that I've looked at, including the ERA 40. There's no trend in their average speeds. So the jet's not getting faster or slower in a systematic way, it doesn't appear. And the waviness of each jet appears to evolve independently of each other. I would say that's true, and that seems to be true in all of the data sets. And the interannual variability of the subtropical jet waviness seems to have a bigger impact in the Pacific, whereas the interannual variability of the polar jet waviness has a bigger impact in the Atlantic basin circulation anomalies. But hasn't been tested for significance. And then in the lower stratosphere, wavier polar or subtropical jet years exhibit intriguing differences in the polar vortex. I don't know if those differences translate to the susceptibility of the lower stratosphere for warmings or not. I don't know. That's a brand new place for me to consider questions, so I don't know what to say about that. But that's what I have for you today. So I'm a little bit puzzled by the lack of uniformity, but that might, I think it is, stems from my naivete about the differences between these data sets. Maybe even in the basic state variables, they can be substantially different in certain ways that you measure things. So thanks for your attention, and I'll take any questions. Greg.
A lot has been said about El Nino and the subtropical jet. So you don't see any increase in waviness during El Nino years?
Yeah, I didn't show that analysis, but I looked at that, and I did not find anything that was that stands out as a correlation between the two. No, it doesn't seem to be. Brad.
So at least for the overall trend, you do see a strong correlation between the polar jet and the subtropical jet in the NSEP analysis.
Yeah,
You showed that you didn't show a correlation on a daily basis, but there must be some point where you begin at some, interannual scale, you must start seeing a correlation if you've got a correlation in the trend, right?
I
It
don't
seems
know.
like there might, if you could look at correlations,
Like for decade averages or something?
Yeah, right.
Yeah. That's a good thing to try. I can try that.
And then you also, I guess I would be a little careful taking every other good point of the reanalysis and doing this kind of high order, PV calculation.
Yeah.
Because you're aliasing features in that high resolution analysis that I'm wondering whether that could impact some of your work.
Yeah, there's something wrong with the regrid that I did in the data. I don't know what it is, but I can tell you that.
But you could just do it at its native resolution, say it's higher resolution and see what you get then.
I already did that, and the thing is that the values are very much higher in both species because the sinuosity is resolution dependent.
Right, and it should be.
Right. But that doesn't tell me the answer to my question.
Well, it tells you that looking at a low resolution analysis might not be pulling out the right information.
Maybe that's what it says, maybe.
So, there's the Mira 2 is a 0.7 degree reanalysis, and you'll see that the waviness is even higher. Because that's this, these PV, that's the raw speed wave breaking. High resolution, low resolution, you lose the filaments, high resolution, you retain it.
Yeah, but that still troubles me because you should still be able to detect some trend, even if you get higher values of waviness. It seems to me averaging over 90 days,
Yeah.
4 times per day, 360
So when
units.
you did the full resolution of the Japanese
Yeah.
analysis, it still didn't show a trend in the...
No, it showed roughly what I showed today. There's no trend in the
No
polar
trend,
jet,
okay.
but there is a trend in the subtropical jet. That's very much like what you get in the NSEP reanalysis. So if I had to right now, and I guess I am, I'm testifying publicly to what I know up to this point, I'm confident that the subtropical jet's getting wavier in the last almost half century. But I don't know what's going on with the polar jet because of the differences in these results.
It was surprising to me that the polar jet had weaker overall winds than the subtropical jet. Does that make sense to you? In the zonal mean, the polar jets, maybe not at those potential temperatures, but it seems like, is that consistent with your understanding of the zonal mean? Or is it because the polar jet has a lot of jet, the subtropical jet is more continuous?
I think that's the answer.
Around the hemisphere.
I think that's the answer.
And you're averaging a lot of gaps.
Bald spots, yeah.
Right.
That's what I would have said, yeah, that's what I think it is. If you did, if you were able to look at individual features within the core of the jet, you might have a stronger wind speed maxima in the cold season in the Pacific, in the polar jet. But even then, it might be about the same. But I think it's that fact exactly. It's more continuous around the hemisphere for the subtropical jet. Zoe?
Is there a way to kind of offer that to characterize how much, like, the amount of gaps within the subtropical or the polar jet for a given year and within the sinuosity to kind of characterize?
The 6-year-old index.
You could, I suppose you could say, once you find the core isotel, that's not going to change from what depending on, that won't have any influence on, your question won't have any influence on defining what the core isotel is. Then you could search again along that length and say, tell me what portion of the length does not have a wind speed greater than 30 meters per second. Right. And then you could kind of figure that out. Yeah, you could do that. That would be interesting. But then what would you call it? You'd say, in places where there is a wind speed greater than 30 meters per second, the polar jet average is this,
Where there is a
subtropical
jet,
jets.
it's wavier or not wavier. You're refining what you're calling a jet.
Yeah.
You're saying, now here's the statistics where there's truly a jet.
Yeah, okay, that's right. I guess that is right. That's something to think about. Maria, then Michael, sorry.
Yeah, because it just makes me think, like, what if the wind speeds are increasing, but you just don't have as long of jets or something like that, or you have more gaps or
Yeah.
something? So I feel like subtracting out those.
Places where they're below a threshold wind
That
speed.
could tell you, give you a better indicator too on, the length or like how much is covered by.
Yeah,
these
that's a
higher
good
wind
idea.
speeds.
I think that's something that I'm ready to do, actually, with what I have already built, so that shouldn't be so hard to do. Yeah, that's a good idea. Thanks. Michael?
Yeah, so this is it's related more to the technique you use that is kind of a curious result. I'm not even sure if it's a result yet because the calculation hasn't been done. But when you do the calculation of the circulation,
Yeah.
you do that on isotropic surfaces.
Isotropic layers, but.
Isotropic
yeah.
layers, right, okay. So if you were to do that on an isotelic surface itself,
Mhm.
right, then you would be seeing both the subtropical and you could do your bundled calculation of the sinuosity. I'm trying to think of the term you use for it.
Aggregate.
The aggregate sinuosity. If you do that on an isotelic surface, surface of constant PV, that circulation calculation you do gives you a measure of the average vorticity contained in that area.
Mm-hmm.
And since it's on a surface of constant vorticity, it also tells you something about the upper tropospheric stratification contained within that. Right, because it'd be vorticity times d theta dp,
Yeah.
giving you the PV. And I'm wondering, from the calculations you've done, you might be able to say something about changes in upper tropospheric stratification within the polar cap or something like that over time. That's just
Yeah, all right, I'll talk to you more about that.
Yeah, interesting
That's
calculation.
interesting.
So
Matt?
to get at the causality, I don't know if people refer to this as the Franz-Fabris hypothesis. I don't know. It's essentially a change in sea ice, averaged over the year, I guess, or reduced sea ice or reduced snow cover. Okay, so you have a really great tool that could be immediately applied as a diagnostic tool in numerical models, right? People could look at waviness using your tool. Is it fair to say, to evaluate waviness for a model, an ensemble in this year versus the year 2099, which those runs exist, straight up? Or is there too many changes globally that aren't just polar sea ice? If you could just change the present to reduce polar sea ice and then evaluate the sinuosity, that might directly address the hypothesis.
Oh, yeah, I guess I see what you mean. If you were interested in trying to address that hypothesis,
Yeah.
you want to change just one
You might be
variable.
able to do it with a numerical model and only change sea ice extent and see
Yeah,
what happens.
yeah, that's a good question.
I think graduate student would like to do that.
Yeah, except I don't have the expertise to mount the modeling part of it. so-
I don't either, but some people are really good at, getting data from NCAR, and I think all that stuff exists.
Yeah, except in climate models, you have to do all your PV calculations yourself. They seem nervous to do PV. I'm not sure why that is. Okay, thanks again for your attention and your suggestions.